Today I talk about one important topics dense set. Okay. Also discuss about dense set now. Dense set plays an important role obviously in mathematics. We also know about this definition of dense set, but we also handle today now again one subset D subset of X. Okay. The of a matrix space is said to is dense in X. It's dense in X. When this subset we call dense in X, so simply here X belongs to X and R greater than 0, then we talk about one open ball the XR intersection D not equal to 5. Then D be dense in X. Okay. So simply we known about it. Then one set D when dense in X when this one happen. Okay. So simply this one happen. Then this one is done. Now we talk about, we also discussed so many things in previous class, and we also known about something about dense set. But now we discuss about A B to dense set. Okay. Given A and B, given that A B be two dense sets in X. Okay. Then what happened? Then is A union B be dense? Let's check about it. Okay. Is A union B is dense? Let's check about it. So what we do? We first do it in this way. A subset of X be dense implies that what dense in X implies that X belongs to capital X R greater than 0. Here Vx are intersection A not equal to 5. So simply again we talk about here B subset of X be dense in X. Then what? Then y belongs to X such that R greater than R1. Okay, greater than 0. B y R1 intersection B not equal to 5. Okay. Then what happened? Then so simply we think about it. That means if any point belongs to X, then obviously we created some neighborhood or some ball, that means um, towards this point or around this point. Then what happened? Then this one intersection A not equal to 5. If B be set, then any point Y here, and we created some, if this, then this one is not equal to 5. Now we talk about if A union B. Okay, if A union B, then we think about one point. Okay, one point from here. Then what happened? A B dense set and A union B is dense. Yes or no? We also check about in this way. Okay, dense means what? Dense means one set is here X. Okay, if we X this one, if we choose any point from this set and drawing some neighborhood around this point, then obviously this intersection A, this one A is not equal to 5. Okay, if we choose here then some point, so X, that means A is obviously, that means fully covered X, or so that means A is dense in X means, that means A and X. Okay, this A is subset of X and obviously contain each point of X. That means this neighborhood content intersection means any point here then this one is in not, that means this neighborhood. We also do some small neighborhood, then this one also obviously, that means intersection, that means this one a not a non-empty intersection. Okay, so what we do here, we do this one, a b is dense, that then a union b, a this one, b this one. Okay, then a, I think this one, a union b, then AB is dense in X. This means any point of X, any point contains some containing in some ball, and then this ball is then ball, this ball is obviously non-empty intersection with A and B. Okay, this one simply, that means if we take any point P from X, then obviously this PR, if R greater than 0 or R2 greater than 0, then PR2 intersection A not equal to phi, if obviously PR2 intersection B not equal to phi. Why? Because A and P are dense in X. Okay, so what happened? A intersection B, what happened in A union B? This one is too easy. Okay, that means if we talk about in this way, this one happened, then we write this way, intersection A union B not equal to phi. Okay, this implies that what, since P is arbitrary, since P be arbitrary and R2 greater than 0 be also arbitrary, or any positive number, then what we get, we also get A intersection B A union B, be dense in X, arbitrary point of X in X. Okay, so what do we get? A union B is dense in X. So simply we talk about it or not? So simply we talk about it. Okay, we just think this one and then we do it. Next we think about A intersection B, what happened? Okay, write this one, this question here. What? A B be dense in X, then what happen for A intersection B? That means, is A intersection B be dense in X? Okay, when this one happen, so simply, if A intersection B equal to phi, then obviously phi intersection something, some ball, some QR. Okay, equal to phi when Q belongs to X and R greater than 0. Okay, so if A intersection phi be in that means phi, then we will not talk about it. Okay, then we can't talk about anything. That means if this one is mutually disjoint set, two sets is mutually disjoint, then we also not talk about anything more. Okay, but if A intersection B not equal to phi, then so simply we talk about this one, Q belongs to X and BQR intersection A not equal to phi. If so similar things, BQR intersection B not equal to phi. Why? Because A dense in X and B dense in X. Okay, so we talk about this one, BQR intersection A intersection B not equal to phi. Then this implies that since Q is arbitrary, point in X and R greater than 0, so A intersection B is dense in X. Understood or not? I think all are understood this portion. Okay, so simply we'll also discuss this one. That means some certain property of dense sets. Okay, A B dense in X, then A intersection B and A union B. What happened in here? Now we talk about one example of proper dense open subset of R. We known about it. Okay, we known about it, but now we think more. Okay, because proper open dense subset of R, proper open dense subset of R, which one is possible? Okay, that means we also think about any, that means z, okay, then R difference z. We think about this two set. Okay, z obviously contain how, that means this one -2 -1 0 1 2 dot 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 these points. Okay, and R difference, that means R difference these points. Okay, so what happened? R difference z obviously, that means obviously one dense set in R. Okay, because we construct any point from this and obviously some neighborhood, then this intersection obviously not that means non-empty intersection. Okay, now what happened here? That means R difference z obviously dense in R. We construct any finite set, because any finite set is closed. Okay, in this way, a1 a2 dot 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 ak. Okay, then this one is that means one finite set which contains k element. Okay, then we obviously talk about R difference this finite set. Sorry, here R difference. Okay, R difference any finite set. Then what happened? Then obviously this one obviously open. Okay, because this one is closed set, contain some union of closed set, finite union of closed set. So this one obviously open set. Okay, now we think about this one is dense, this one is dense in R. So we talk about one open set dense in R in this way. Okay, so this one, if we talk, that means let y belongs to R, then obviously be y R, R greater than the intersection this R difference this one. Okay, not an empty intersection. No problem at all. Okay, all are understood, I think. Next we also talk about more portion also, as that now, and now also discuss another portion. Okay, that means we known about it, discrete matrix space. Okay, discrete matrix space we also known about it, and then subset of discrete matrix space we also think about this one. Okay, that means any subset of a discrete matrix space is closed, hence the only dense subset is what? The whole space. Okay, then dense subset dense subset of discrete matrix space. What we talk about in this way, any subset of matrix of a discrete matrix space is closed. Any subset of a discrete matrix space be closed. Okay, so only subset of such a space is the whole space. Okay, that means only dense subset of discrete phase is the whole space. Okay, why we know about it so simply? That means discrete matrix defined in this way, dxy equal to 0 1 when x equal to y, x not equal to y. Then what happens? That means we talk about in this way, if two distinct point is here, then their difference is 1. Okay, then we talk about one neighborhood less than 1. If r is less than 1, then this one is just singleton x. Okay, this neighborhood intersection this space, obviously this singleton one, not more than that. Okay, then this one is, that means this neighborhood intersection, if we talk about this one, then this one equal to 5. then obviously that means no set is, that means if x, then this one is possible. If x different something, then this one obviously going to, that means not dense here. Okay, so only dense subset is this one, this whole space x. Okay, now also then talk about more example of dense subset. We know about it also, and in previous class we also going to this one, dyadic rationals are dense in R. We know about it, rationals from in this way to Mn, or Mn belongs to Z. Okay, then is dense in R, we also known about it, and we think that means we also doing some problem of this. Now we also know more, but today we not discuss more problems here. Okay. But just one sequence in L2 we also discuss now. Okay, we also discuss one sequence in L2, and obviously then another problem. Okay, so we now start here. The set dn of all sequences x equal to xn whose terms are rational, and xk equal to 0 and xk equal to 0 for k greater than n. Okay, now let d equal to union of n belongs to n dn. Where is dn is obviously bijective with where is Dn is obviously bijective with Qn. Okay, and hence it is countable, because we know about it. Qn is, that means countable, so this one is countable. Now obviously, that means D being a countable union of countable set, that means D is countable. D being a countable union of countable sets, so D be countable. Okay, not a problem at all. Now we just think about T and all sequences such that whose terms are rational and x equal to 0 for k greater than n, and x all our other terms are rational. Okay, then what happened? Then we talk about this one. D is dense in L2. Okay, what we talk about? D is dense in L2. We think about this portion. D is dense in L2. Then what we need to show? We need to show what? So that given any x belongs to L2 and epsilon greater than 0, we can find y belongs to D. We can find y belongs to D such that norm of xy difference to less than epsilon. Okay, if we see this one, then we talk about this portion. D is dense in L2. Okay, so first what we do here in this way, we write now, since x belongs to L2, then what happened? Then there exists n belongs to natural number. Okay, such that summation n equal to 1 to infinity norm of x n square less than epsilon square by 2. Okay, then again what we that means considered this one, just x belongs to L2 means this one. Okay, that means square of each term, modulus of each term square sum is less than one finite number. Okay, but this one not 1 to after some time, that means after n plus 1 to infinity. Okay, then we also think about this one. Considered v belongs v in Rn. Consider v equal to v1 v2 vn belongs to Rn. Okay, and since Qn is dense in, is our portion, since Qn is dense in Rn, then what happened? Then there exists R equal to R1 R2 Rn belongs to this Qn such that v difference are this square less than epsilon square by 2. Okay, since Qn, that means V belongs to this Rn. Okay, then we think about that R belongs to Qn and this one is happened since Qn is dense in Rn. Now we obviously define a sequence. We define a sequence. Okay, we define a sequence Y such that yk equal to rk, such that yk equal to rk, 1 less than equal to k less than equal to n, and yk equal to 0 and yk equal to 0 for k greater than n. Okay, then what happened? Then obviously y belongs to L2 because y is in this way r1 r2 dot 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 rn and 0 0 0. Okay, so y belongs to L2. Okay, now what we have then, so what we known in previous, I also think about here, right? X y difference, this one equal to what? Equal to k equal to 1 to n. Here x k difference r k square plus here k equal to n plus 1 to infinity norm of x k square. Why? Because obviously y equal to 0 0 0. Okay, after n plus 1 term, then this one is done. Okay, now what we do, we know about this one is less than epsilon square by 2, this one is less than epsilon square by 2, so this one is, that means from this we also think about this one. Okay, and from this we also think about this one. So this one is less, that means norm of x difference y2 less than epsilon. This implies that D is a countable dense subset of L2. Okay, that means D is dense in L2 and this implies D is a countable dense subset. Countable dense subset of L2. Okay, since we know about it, this one is countable first and obviously then dense subset of L2, so this one is countable dense subset of L2. Also now prove this one. Okay, one example of dense subset in L2, so simply this one is, we prove it. Now we erase that portion and going to further discussion of another topics, one important lemma. Okay, I think this one is understandable, too easy. That means we define a sequence and then this one is, we also construct some union of this sequence, then we also find one set and this one is dense in, then countable set dense in L2. Now we discuss about one lemma related to these topics. We first write the statement of this lemma. Let s equal to let s equal to m plus m root 2 plus n, m root 2 plus n. Here m belongs to z. Okay, let AB belongs to R, let AB belongs to R, be such that A less than B, be such that A less than B. Okay, then what happened? Then there exists and S belongs to S, then there exists an S belongs to S, then there exists an S belongs to this S, okay, such that A less than X less than V, A less than S less than V, okay. In other words, S is dense. In other words, S is dense in R. Okay, so we talk about this portion. Okay, how this was is happen. S is dense in R. We define S in this way, and A belongs to R. Then we find this one. This means that S is dense in R. How we prove it? Okay, we know about it. How we prove it? Also discuss now. Now we're going to prove of this. Right, prove here. First, if xy belongs to S, then what happened? And k belongs to Z, then have x, then x plus minus y k x belongs to this S. Okay, this one is too easy. And let nm equal to what? Equal to this one, m root 2. Okay, that means the greatest integer less than or equal to m root 2. This one equal to the greatest integer less than or equal to m root 2. Then what happened? Then 0 less than equal to m root 2 difference nm less than 1. Okay, this one are happen. Now we're going to further. Now we'll see about that. It is saying that means n plus m root 2 equal to n dash plus m dash root 2. This implies that n dash equal to n and m dash equal to m. Okay, now we're going to be further discussion of that. Let Sn equal to what? Right here m root 2 difference in m. Okay, then obviously S, we write here Sm because here all are function of m. Then what happened? 0 less than equal to Sm less than 1. Okay, and Sm belongs to this S. Okay, now also if m not equal to m dash, then Sm not equal to Sm dash. Hence we conclude that Sm dash is an infinite subset of, hence Sm m belongs to Z is an infinite subset of S intersection 0 1. Okay, now we erase this portion and going to further discussion of that. We have to show that S is dense in R. Okay, then what we do, we just talk about epsilon greater than 0, given epsilon greater than 0, then we partition 0 1 into k equal parts, into k equal parts, so that each subinterval has length less, so that each subinterval has length less than epsilon. Okay, now at least one of these subinterval must contain two distinct elements. At least one of these subintervals must contain two distinct element. Okay, two distinct elements Sm and Sm dash, okay, of S intersection 01. Then without loss of generality, let us assume that Sm less than Sm dash. Okay, then what happened, then what we find, then 0 less than Sm difference Sm dash less than epsilon. Okay, now since Sm difference Sm dash belongs to S, so what happened, we have shown that what, given epsilon greater than 0, there exists S belongs to S with 0 less than S less than epsilon. Okay, this one we have to show that. Okay, then this one there exists, and that means we also find this one. Okay, now fixed, that means fixed epsilon greater than 0 be such that b minus a greater than epsilon greater than 0. Now we can find one S. Okay, we find one S belongs to this capital S such that 0 less than S less than epsilon. Now we claim that there exists n belongs to Z. We claim that there exists n belongs to Z, okay, such that A less than n, S less than B. Okay, now n be the least integer k such that A is greater than A. N be the least integer k such that k is greater than A. Then what happened? Then it is our portion. And we're also going to this. Okay, then n minus 1 is less than equal to A less than ns. Okay, and obviously we claim that ns less than b. Then b difference a less than equal to what, ns, okay, difference n minus 1 is. Then this one equal to s less than epsilon. Now here a contradiction arise. Okay, then what happened? If we talk about this one, then one contradiction arise, that means p minus 1 a, we talk about this one, and here what happened? P minus a less than epsilon. Okay, so we also do this, thus a less than nx less than b, this one is happen. Okay, now now since ns belongs to s, we erase that portion. Since ns belongs to this s, so what we find? So we find that there exists one c belongs to s such that a less than c less than b, so s is dense in r. Okay, so we also easily seen this one. Now we're also going to one another, that means another important topic. This one is sum of two closed sets need not be closed. This one is the conclusion. The sum of two closed sets in R need not be closed. Here we talk about this one, and that means we think about this one. This is equal to n plus m root 2. Okay, where n m belongs to z. Then this singleton n and singleton m root 2 all are closed in R, but this S is not closed because S is dense in R. That means S closure equal to R, so S is not closed here. Okay, we're also going to one, that means one important topics here is since this one is closed but S is not closed. Why? Because S closure equal to R. Okay, so we also discuss this one. S is dense in R, and obviously one, that means important corollary from this, sum of two closed sets in R need not be closed. Okay, now stop here.